Okay, welcome to the August 31st OMR Architecture Meeting. Today we have the third installment of Mark's walkthrough of JitBuilder 2. Today he'll be taking us through some of the code that he's written to try and solidify some of the concepts. So I'll turn it over to him.
All right. Okay. Can everyone hear me okay? Can anyone hear me?
Yes.
All right. That's good. I have two microphones in front of me. I have no idea which one's live or if both of them are live and confusing. Anyway, let me just start sharing here. Any fit of, yes, okay. Sorry, Daryl. Kick you out.
No problem.
All right. Can everyone see the travesty of my Visual Studio window?
Yeah, I want to zoom in more. It's very tiny.
That's very large. How about that? How's that work for people?
Good.
Can I move this over?
Press Control B.
Control B.
Or Command B. That'll move the thing away.
Ah, better. Thank you. Unless I need to open another file.
Command B again.
Yeah, I got it. All right. So, the last two meetings, I basically assembled a bunch of slides and included some code snippets on slides, but really didn't, and tried to kind of take you through and give you a flavor for how some of the things were put together. But it struck me afterwards, or actually during some of the questions, I think afterwards, that I'd never really given a full sort of summary of what an extension is or looks like. And so what I thought I'd do today was just pick up the most substantial extension that exists right now, which is called the base extension, and show you what all is in that thing and what all it defines and how it adds it into the general compiler infrastructure. So if you remember, extensions are basically like pluggable capability. You can plug that capability into the compiler. So the compiler, the base compiler, doesn't have any notion of things other than the base types that it defines itself. And extensions can come along and add new types, new symbols, new operation types, new compiler return codes, etc. So let's take a look at how some of that works. So this is the header file for the base extension. And for now, I've kind of provided some convenience header files that allow you to not have to go and figure out what all things you exactly refer to, which obviously has a compile time impact, but it's much simpler to figure out which header files to include. So there's a jvcore.hpp, which is basically the collection of all the header files in the core JitBuilder 2 or JB2 project, even if you don't use them. And then base actually should not depend on this header file anymore, but for some reason it's here. So please just ignore that line for now, and maybe we'll discover why it's there as we roll through it. The base infrastructure I've put into the same OMR JitBuilder namespace that the original JitBuilder code was in. I've recently been thinking about changing that to having just a single JB2 namespace, but outside of OMR, just to simplify actually reduce the size of the the number of symbols that get created when you create these libraries, but that's a minor thing. And then the sort of common way that I've been implementing different extensions is to give them all their own namespace, sub-namespace inside there. So the base extension has a namespace called base, and so all of the stuff that's in the base extension goes into the base namespace and isn't supposed to pollute other things. I like to write header files that don't depend on other header files as much as possible, notwithstanding all of this stuff here. But it doesn't include any header files from the base, any other header files from the base extension. So I'm trying to reduce dependencies on the header files in the base extension, which means that I just do a bunch of forward declaration for all classes, and that avoids getting stuck into dependency hell trying to figure out which header file to include to get the thing that you need. So you can kind of forecast some of the things that you're going to see in this base extension. There's all the primitive types that used to exist in JitBuilder as standard things. There's the case guy, which is used that creates switch operations. There's pointer types. There's types associated with structs that have fields. Union type, although I don't actually use this yet. Union type's actually kind of redundant in JitBuilder in JB2 for struct type. And then switch builder is kind of an interesting thing. Yeah, let me skip.
Are these all here because this file uses these?
This header file references these types, yes.
Okay, no.
It references them. It doesn't require the actual definitions for them. All right, and so we finally get to the actual base extension class, which is an extension of a thing called, subclass is a thing called extension, which is where all the core functionality for building extensions exists. So this base extension object, remember, is an object, a singleton object for the plugin that basically represents all the capability in the plugin in essence. So whenever you want to use something from the plugin, you end up calling something or referencing something off of the base extension object. And that means you can pass around this base extension object to people, and then they can use the capabilities in that plugin very easily. So one of the things that it depends on is the core extension, which is it's defined by JB2. I'm not going to go into details on that. It's a very simple extension, so I'm not going to bother looking at it. We looked at some of the allocator stuff and how you introduce that into the class. You can see the JBAlloc thing here and the dynamic alloc only helper to create the constructor that automatically takes an allocator object, so you don't have to think about it, etc. in this constructor. It has a name, which is the name of the actual extension. It has a semantic version associated with it, so there is a way of saying I depend on a certain version of this extension, and it can distinguish between minor and patch updates to the extension that still support the same API versus major version updates, which would break the API potentially.
That string is your string, not a standard C?
Semantic version is a class.
No, string.
Oh, string. Yeah, that's my string.
Okay.
Yeah, sorry. Yeah, that's my string.
Okay.
Which I'm actually in the process of ripping standard string out of. Thanks to Darren for Devitt, sorry, for pointing out that I needed to do that. Anyway, or the pain that I would have when I tried to do that. Right, okay, and then as I mentioned, there are, this object has various things kind of hanging off them. So for example, the primitive types end up becoming fields of this base extension object. So there's a no type guy, which is actually from the core extension, but we cache it here just so that it's easy to get at. It's kind of like the void type. An 8-bit integer, 16-bit integer, 32, 64-bit integer. I renamed JitBuilder's float and double to float 32 and float 64 just for consistency with the integer ones. There is still an address type, which is an untyped pointer in essence. And then there's a special guy word, which gets initialized with, based on the platform bitness to either in 32 or in 64 usually. There are some helpers here to create some other types. So I don't know why I have only pointer 2 here, but anyway, these are, or I guess this is the core thing that helps you get a pointer type for a particular base type. And you have to pass in the IR object that the type is supposed to be associated with. And here's an example of that location macro, which passes in a file name, a line number, and the function name relatively automatically, so that if something goes wrong in the construction of the pointer 2 type, or if something happens later on that you want to get access to, it knows where you called this from in your code base. Right. So types is one set of things that can get created. And again, this is just a header file, so it's just showing you what things are going to get created. I'll go through the CPP in a while that'll show you how those things actually get created and allocated and stored there. Actions, I haven't really talked about, and actions is really just a number, an assigned number that corresponds to the various operation types that you can create. So there's a constant operation which will have this action ID associated with it. There's add, sub, mul, all the sort of operations that used to exist in JitBuilder. Basically, if you ask an operation what its action is, it will return you this action ID. And different extensions, because they add new operation types, need to have this action ID that differentiates between the operations that extension can create, so that you can always identify which ones, what a particular operation is, in essence. So there's a whole bunch of things.
And the naming convention here is the lowercase a there means that this is an action? Just
an action, yeah. Okay. Yeah, and you're right, that's just a convention. It's just a naming convention to keep things sort of somewhat sane. And then you don't have to, but I've divided these up into some sections to like memory actions, control flow actions, etc. So that's the full set of actions that the base extension currently defines. So it's not obviously equivalent to the full set of operations that JitBuilder used to support, but the intention is that most of those operations will probably show up here eventually. And there are some new ones compared to JitBuilder. So I didn't used to have a thing called load field and store field. These used to be kind of load indirect and store indirect. So they're now more referencing fields. So load field and store field operate on, in principle, a struct as a value, whereas load field at and store field at go through a pointer, dereference it to be a struct, and load the field at that end. Otherwise, this is quite similar to these different operations that were there in JitBuilder. Another thing that you need to be able to add are return codes if things go wrong, or error conditions that this extension can detect and report. So there's a way of registering with the compiler to say, hey, I need a return code for this condition, and then that condition gets stored on the base extension object so that you can go and say, was the return code this, right? So very easy way to do that. And then finally, there's a section of operations. So these are functions, member functions on the extension object that allow you to create operations of those same types that we had the action IDs for before, right? So you can create a constant in this builder at this, I don't know why I didn't put a B there, and a constant which uses this literal. Or you can put an add operation in this builder and add these two values together and overturn the result of the add, and etc. All of them are annotated by location, so you can, again, if something goes wrong, or if the wrong operand or operand types are provided to the operation creator, it can, and it detects that there's a problem. It can record the location that you called this thing from, so you can find the whoever it was that supplied the wrong thing, basically. In terms of control operations, most of them are fairly, like the simple ones are fairly, easy to kind of understand how they work. All of these functions, sorry, it keeps showing me all the details about things. All of these have as their first operation the builder into which the operation is supposed to be inserted. So in JitBuilder, you used to do B arrow go to B arrow if compare equal B arrow if compare equals 0. So it used to be the builder object that you use to create these operations. But it's now, since you're now having these extensions which you can load or not load, it's the extension object that has to create these. So you have to tell it which builder you want to put it into. So I felt this was more flexible than having something like an insertion point that you go and say, now I want to create operations over here, and then all the calls use that insertion point, and now I want to put code over there. But it does mean that you have to pass the builder all the time.
Sorry, Mark, perhaps you could explain why there are two builder parameters to each of these, or to many of them.
Yeah. So the reason why there's two is because so for GoTo, for example, B is is the builder object in which the go-to operation should be created, and then target is the one that it should, it's intending to direct control flow to. Right, so it's actually inserting a go-to instruction into builder B that says go to target. Does that make sense?
Yeah, I understand the things as they relate to go to, but I don't understand how a builder is the right representation of a target then.
Okay, so a builder object is it's basically a label with an open curly and a set of operations and a closed curly. That's what you can think of as a builder. That's a builder object in a nutshell.
So it would.
So you can branch to a builder. You can branch to a builder, and it will perform the set of operations that are in the curly braces. Or for operations, if you have to insert an operation into a builder, it goes into that sequence of operations.
So in C or C++, we might call that a block.
Yeah, you might.
Well, I guess the builder is the machinery responsible for building blocks, and so it seems strange to use the same name for both concepts.
Sorry, the same name for both concepts, both the label and the block.
You agreed with me that block is a name that we might all understand, given some C or C++ background, or even Java, right? And so the block is the thing that we're growing, and the builder is the toolbox that we're using to make it happen. And so, like I say, I might expect the go-to to take a builder, that's where the tools come from, and a block, that's where we want the results to go. And so do you understand my?
Yeah, I mean, I understand what you're saying. I guess this is so one of the thing. This is something that we inherited from the JitBuilder API. So it's a long-standing mistake, if you want to, in the API for JitBuilder, in that a sequence of operations and the label to the operation, like the thing that you use to build the list, as well as the thing that you are having instructions branch to, is called the same thing.
Okay, so you're putting in the builder, in the first or the second parameter, or well, the thing called B, receives the go-to instruction, that if that go-to is executed, it ends up at wherever target means.
Correct.
Okay, and I suppose, okay, as I think about it more, maybe this makes more sense than I thought. The target is something that could also be expanded with other instructions at a later time in the execution of the build of the application.
It is representing a full code path, like a region of code. You're right, a block. I mean, it is a block of code, but I guess we share the same concept to simplify the number of different things we've got. But I can get that might be confusing the first time you see it.
Yeah. Okay. Thanks, Mark.
Yeah, sure. So one of the things that did change between JitBuilder and JB2, JitBuilder 2, I guess, are things like how if then else and for loop operations work. So it used to be the case that you would pass in, you could create or not, it would create automatically for you, builder objects that would represent the body of the for loop, or the if you needed a break, a builder for the break, or a builder for the continue as labels to be able to jump to go to, you would pass those in yourself. Now you don't do that anymore. The creation of those builders, because in JB2 they're called bound builders. They're actually created by the for loop itself, so you can't pass them in yourself anymore. And the way that you find those things is through this for loop builder object that gets passed by. And notice this isn't a pointer; it's just passing back a whole thing by copy. And essentially, for loop builder just basically records all the information about the for loop that you might need to know. So it has the loop variable in it, it has the initial, final, and bump in it, it has the body builder, it has the break builder, the continue builder, etc. So as you're working through this, as you're building up the code inside the for loop, you can just access this the returned for loop builder to figure out where to put things and how to get to the various bits and pieces of the for loop that's going to be constructed. And the same thing for if then else. So you don't pass in any more a then path or an else path. It's the if then else builder creates those in principle, and then if you need to put code into them, you can ask the builder object that you got back, hey, what's the builder object for the then path, and so I can insert operations on it, etc. Switch has a flip side, so I don't know. I'm not perfectly happy with this notation or nomenclature, I guess, that I've chosen. That you, in some cases, you get a builder object back, and in some cases, you pass a builder object in. So for switch, you pass in a switch builder, because in the case of a switch, you kind of have to be able to all of the case things. You have to kind of build them as you go and pass them in. So the switch builder object in this case provides a mechanism for creating all of the switch conditions that you might need, that you want the switch to have, and then it kind of builds the switch from all of that information, as opposed to the other way around, because it's harder with a switch. It's harder to say which is the switch condition that I mean to get the builder object for, or what are the values in the switch that I'm switching on, etc. So it kind of went the other way around. So I'm not perfectly happy with this, but it's the way it is right now. And kind of open to ways to improve that for sure.
This brings up a different question for me, if you
Okay.
don't mind me interrupting again, Mark.
Yeah.
So in this extension, you're defining all of these concepts that, and my question is, do they need to correspond to any kind of known language or whatever? Like, are the concepts limited here at all, or could I invent something that might make sense in the Waterloo Systems language, which I used in university, which has a guess statement, for example?
Yeah, so I mean, these particular operations have a particular kind of semantics associated with them. One thing that's they sort of have a way of checking their own semantics. Like, for example, all of these operations, and including the arithmetic operations, basically assume, in most cases, it's not completely true, but bear with me, that like the left and right values all have the same type, like exactly the same type. So one of the things that gets validated in at least some of these operations right now is that left type, the actual type of the left value and the type of the right value are the same. And if they're not the same, it will not create an operation. It'll throw an exception with one of the return codes that I showed before. But there are ways for other extensions to come along and tack themselves into that process and allow themselves to allow other combinations of things to be validated. So the usual example that I give for this is what if somebody created an extension that handled complex values, and I wanted to be able to reuse add with complex values instead of integer values, for example. The complex extension is allowed to reuse add, and there's a mechanism whereby it can add its own kind of operation checker in there to say if left type equals right type and that type is complex, that's okay. And if there and it will still any other combination of types won't be. Well, the validation of types will otherwise be unchanged. Let's put it that way. So the base extension is going to provide some kind of validation for the types that it knows about, and the operations that it understands how to handle. And then another extension can come along and say, oh, I also know how to handle these combinations of types, so allow those to be created too, if that makes sense. So in your example,
That
Sorry,
sounds
go
like an extension in a different dimension than what I was thinking about. But extensions sort of in the type system. I was talking more extensions in the control constructs in the language that you're thinking
Right.
of.
Right. So I mean, I think you could.
So I mean,
I'm not sure I understand the example that you're referencing in your thing, but like in principle, you could create your own extension, which would define what that control construct is, and you could build that control construct out of the operations that are in this extension if you wanted to.
Right. So I guess another way to ask my question is: imagine that nobody had ever heard of a switch statement before.
Yep.
You could manufacture this function called switch here that does what you want it to do.
Right. Yep.
Okay.
Yeah. So I mean, essentially this base extension. It's not part of the core JB2 functionality, right? Like this whole base extension is completely optional. You don't have to load it into your compiler or not. So the core function, the core compiler has no idea of almost any operation at all. So all of this is the base extension adding in support for creating and manipulating these kinds of operations that it knows about. So if you had your own extension, you could also do that for whatever operations make sense for your language. Make sense?
Yep. Thanks.
Okay. All right. So control operations, a bunch of sort of memory-related operations, most of which are familiar. I won't go through these in great detail. There are then some pseudo operations. So these are kind of like, you think of them like helpers. They don't actually create operations called constant 8, constant 16, constant 32. But what they do is they take a different set of parameters and construct some IL that is, or IR that's associated with it. So in the case of these constant ones, what all of these things do is they automatically create a literal object of the appropriate type, and then they call back into const to create a const operation that takes that literal. So it's like a helper, basically. So you don't have to always create the literal object yourself. You can just, if you have a byte or a 32-bit value in your hands, you can use one of these to just create it directly without having to, create sort of some of all the intermediate stuff. That's not the intermediate stuff, but anyway, I think you know what I mean. And basically, it has one of these for all of the sort of base primitive types. There's a way of creating a 0 and a 1 for types. Not all types support the creation of a 0 and 1, so it's possible that this will fail if you ask for a 0 or 1 of a type that doesn't. Like if you have a pointer type and you ask to create a 1 value for a pointer type, it will throw an exception to say, I don't know how to do that. But if it's int 8, int 16, float 32, whatever, all of those know how to create a 0 and a 1 for themselves. So it's just another kind of easier. Some of these came about because when you look at some of the JitBuilder samples, it's repeatedly, it's like, I need a constant 1, I need a constant 1, I need a constant 0, I need a blah, 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 blah. So these ones just make it a little bit simpler to create those kinds of things. And then some of the other helpers here around, if you needed to access an array, for example, it kind of folds together a couple of the constituent operations. It combines load at with an index at operation, and you don't have to provide as many things. You don't have to hold on to the intermediate value yourself, etc. So it's just a little bit of convenience for some of the common uses for some of the pointer manipulation stuff. And then that functionality that I mentioned before for being able to add handling of different kinds of types is done right now. It's done with a thing called a base extension checker, which is a class that just kind of knows how to validate operations of this type. This is a pretty ugly hack right now. I don't like this. I'm going to rewrite this at some point to use the add-on infrastructure that I mentioned in the previous talk, but right now it's built on this base extension checker thing, and I'll show you what it looks like in a sec because it's at the bottom of this guy. And then yeah, there's just a few other things. the actual version of the current code. So I haven't been doing, I don't keep this up because it's such an intermediate step right now. There's such a basic condition right now. There's no sense in actually maintaining the versions. But once this gets to a point of becoming useful, and if other people actually start picking it up and using it, that would be the point at which we would need to start maintaining these version values so that the semantic version checking could be used. And then just pointer back to the previous call where I talked about the kind service and how it helps manage the various extensibility types. This is how the extensibility so basic extension is an extensible type. So this is what helps register the base extension into that extensibility mechanism. And as base extension checker is pretty bogus looking. I'll show an example of how this gets called when you're creating. But it's basically those functions that I showed before that create operations. They will call into validate add on a checker object. It goes looking for any checker objects that are around, and it will call validate add. And if somebody validates it and says yes, it's valid, then that's great. If somebody validates and says it's bad, then it automatically calls a fail validate, and which will create an exception object and throw it, and using some of those compiler return codes that I showed at the beginning. That's basically how that works. And then sort of some of the other classes like the for loop builder, I just mentioned it's just kind of a holder for all of the useful variables associated with a for loop. If then has the same thing for all of the useful things associated with the if then else, so it knows which value is used to determine which path is going to be executed, and then it knows which paths where the then and else path are, etc. And that's basically that. So let's switch to looking at the CPP file. So obviously it needs to know more about how things are actually implemented and what things can be used. So there's a whole whackload of these guys. I didn't really have to include these, but I didn't. I guess they could have gotten it all from here, but they're there anyway. So there's going to be a whack of imports here, some of which won't be necessary, but a lot of the base extension files are actually included here because I've separated out. The operations are in various files for arithmetic operations or const operation or control operations or memory operations are all in separate files. Some of the symbols that get created and the types that get created are all separated off into separate files. So this is really just the extension object definition, and there are other classes that it's going to use and reference as it goes. Again, this is, from the last presentation, we talked about how the allocation stuff is all set up and how the kind service stuff is set up. So it's just straightforward there. We have to create the actual semantic version that's here, which are these are the values that were populated from the header file up there. In this, that's why I had func. Interesting. All right. So in this version of this file, base is looking like it's dependent on func, the func extension, which is the extension that allows you to create IL for functions, right? So callable things that have parameters and local variables and can be called and can call other functions, etc. And so this mechanism here is just the way of documenting what's the dependency that's needed, like which func, which version of the func extension is needed by this version of base. And then normally what would have happened is if there was actually a dependency, which I think I've removed without removing this stuff, is in this function here, which I'll talk about in a minute, before creating the base extension as part of that process, it would verify that there is a func extension loaded, or it would try to load a func extension with that needed version. And if it couldn't get one, then it would fail to load the base extension as well. The expectation of the JB2 compiler infrastructure is that your extensions are stored in shared objects, and those shared objects have a particular entry point called create, which again takes a location and just the compiler that the extension's being loaded into. So it gets passed in by the compiler. When somebody calls load extension on the compiler and gives it the name of this guy, it loads a shared object and calls this create function, passing in the compiler object, and it's supposed to pass back either null or an extension, the valid extension object for this extension. So modulo the lack of error checking here, this is allocating a base extension object and returning it basically. So this is the mechanism by which the singleton base extension object gets created, and then nothing else is supposed to be able to create it. So or nothing else is supposed to create one of these things, although that's not really mandated somewhere very well. All right, and then so you notice that all of those fields that were defined on the base extension, in the base extension class, are all const. That means they all have to be initialized in the constructor, which means that it's the constructor that has to go and initialize and register all of these things with the compiler object so that they get installed. So the core extension, as I mentioned, is something that the compiler creates. So you can just ask the compiler for the core extension, and this is just caching it so that it's easy to get access to. The various types need to be created, and then as part of these things being created, it doesn't show it here, but in the base class of all of these types, which is type, what it does is it registers the created type object with the compiler so that it can get access to it. And there's something wrong with that right now that I have to think about more, but I won't point it out. Sorry, so all of these types plus Word, this is where Word comes in. This is not a great way of doing this, but I couldn't think of a better way to do it off the top of my head. Eventually, this will need to be not the compiler's. It says platform word size. That really needs to be sort of the code platform word size, is what that should be, as opposed to the compiler platform word size or the client word size. Anyway, that's probably more subtlety than needed. The operations are all created by registering the action and giving it a string name. So these all get passed in to the compiler. What this boils down to in the end is the compiler maintains a list of actions that have been registered and assigns consecutive IDs to them in a 64-bit namespace. So if somebody manages to create more than 64 bits worth of operations, the world will be in more trouble than I'm worried about. So this just basically bumps a number, and the compiler holds on to and creates. So if two base extension objects got loaded with two different compilers, they could have different action IDs, but you would always use the base extension object and access what the type is or what the number is here, rather than referencing any specific number. And so all of those go through exactly the same process. It's very similar for return codes. So register return code, again, goes to the compiler, associates a string name with an ID that it just bumps an ID and returns it. All of these IDs have different namespaces. So there's one file in the core compiler infrastructure that's called ids.hpp, and it just has a whole bunch of type defs that give ID type names to UN6014. So they're all right now 64-bit types, but they could be changed independently, and it's all typed. So action IDs and compiler return code IDs and value IDs and type IDs and symbol IDs, etc., are all independent namespaces and properly checked. And then checkers is that list of checkers, so it gets initialized with the allocator that needs to be used to manage the list. Even though it's this first one is null because checkers is an embedded object in the extension object. So this isn't a dynamically allocated list object. If it was, then this wouldn't be null, it would be A. So it would be allocating the object with A, and you'd have to actually allocate it with that A. Let's not talk about that. Right, okay, here's some of the extensibility mechanisms for the base extension at play here. So this call goes back to the compiler in the end and says, for anybody who creates an IR object, I want to be notified of that object creation. And similarly there's a class called IR cloner. And that's because the base extension creates new types that need to be tracked in the IR, and what it does if one of these objects gets created, it tacks an add-on in that's specific to the base extension to be able to track those things. Here's where maybe this is why I've got it. So this code is how you would look up an extension. So this one's trying to look up the function extension basically and getting a pointer to it. So if it was able to look up the function extension, i.e. if the function extension has been loaded, then it's going to go and create a function extension specific add-on using, it's going to add it to that extension object itself. I'll show you what that is in a sec. If it hasn't, if that extension hasn't been loaded, it might just not have been loaded yet. So what it does is it registers to see if anybody ever creates a function extension object, it wants to get notified so that it can do this create add-on process here. And I will go through, I think, some of that here. Right, so create add-on. So create add-on is this, is the thing that gets called by the compiler if an object of a particular type has been created, right? So essentially, when a function extension or an IR cloner object gets created, it calls back into the compiler object, and the compiler object says, hey, this extension wants to watch for those allocations. So call that extension arrow create add-on and pass the object that got created, or the extension that created it. Actually, it's the object that got created. So create add-on is this sort of entry point, which I've leveraged in the object itself too here. But basically what this is saying is that if an IR object got created, then it will get called with that IR object. E will be that IR object. If it got created, if it's being called because an IR cloner object got created, it will pass the IR cloner object here. And if it's the function extension has just been created because it's been loaded, then it will pass in with the function extension. And so the function, so I'm not super happy with this dispatch mechanism either, but it's not too bad yet. Have to think about ways to make this a little bit more clean. But anyway, right now it just uses the extensibility tests to say, you know, is it an IR object? Okay, it's an IR object. Create the base IR add-on object and attach it to that to the base object, the base IR object. Is this what do they call that? BC. Anyway, if it's a function extension object, then it creates the base function extension add-on object and attaches it to that guy. If it's a base IR, if it's an IR cloner object, then it creates a base IR cloner add-on. And these are all classes inside the base extension that add stuff on to each of these base classes, and it just attaches it on. And like I showed in the previous presentation, once it's been attached, anybody else who gets their hands on one of the base objects can just say, give me the add-on of this type for that root, for this object, right? So someone can say, if somebody else has this IR, let's do the IR. So an IR object, so they're handed an IR object pointer, you can just say, give me IR arrow add-on, base IR add-on, and it will hand you back the add-on object if it exists, or null if it's not there. Okay.
What is the connection between add-ons and extensions? Like, are extensions the interface API, and the add-on or the actual things you can do?
Sorry, what's the connection between extension and add-on?
Yeah.
So extension is just it's a type of object that represents a set of pluggable capability to the compiler, right? So The base extension is saying, here's all this stuff I want to inject into the compiler and have the compiler be able to generate, that extension's IR and be able to do its optimizations, its analyses, etc. The add-on thing is, it's basically like a mix-in. Like an add-on is a mix-in for, you can, like, I want to add this capability into that object over there. And so it's a way that JB2 allows you to establish a connection between the mix-in and the object that you're mixing it into, right? And provide a way to get at the mix-in from the core object, right? So it's not part, you can't, C++ doesn't allow you any way of dynamically extending the API of something else, right, without creating a subclass. So this is a way of adding API into an existing object without making it a subclass.
So the add-ons could be for anything, like an extension can have an add-on.
Yes, an extension. In fact, that's what that function extension add-on is, right? Because it's anything that's extensible can have an add-on. An extension is an extensible class.
Why would you want an extension to have an add-on versus just say the extension has these extra capabilities? So
the reason why I did it with the base extension, so it's not actually needed anymore, which is why it's not a great example, but let me talk through it. So the function extension adds things like load a parameter, load a local variable, store a local variable, right? The base extension adds things like add, mul, etc., but add's the only one that really matters. So if you wanted to create a thing like an increment operation, you need to be able to load something and you need to be able to add something. So you need bits from both, in essence, right? And so the way I did that was, so func can't have it because it doesn't know how to add, but it knows how to load and store. Base, once you know how to add, it basically says, if there's a function extension around that knows how to load and store, tack in this thing which knows how to load and store and add, right? So in that way, somebody that knows about this can say, I want to load both of these things and I want to be able to use inc, and I'll put it on the base extension. Or sorry, I'll put it on the func extension. And the reason why that's useful is because it means that the base extension doesn't have to depend on the func extension. Notwithstanding the code that I showed before that looks like it depends on it, it doesn't actually depend on the func extension. And so that means you could, at some later date, if some intrepid person comes along and does it, you could use the base extension to compile things that are not functions, that are traces, or that are just basic blocks, or there are other things, right? So I don't have to have func around in order to use basic arithmetic and load store values. No, not load store, sorry, basic arithmetic.
So this add-on here that you're just talking about, that's added on to the function extension?
Yeah.
Okay. And then it knows that it needs to depend on the...
Yeah, and the reason why I initially did it and don't actually have to do it now, the reason why I did it before was, well, I guess I still sort of do, but I used to have that inc function used to specifically take a local symbol, which is something that's specifically defined by func and doesn't exist in the core implementation. So base needed to have func in order to reference local symbol. But like in principle, you can do inc with any symbol, right? So it doesn't have to be a local symbol. So I just downgraded it as symbol, and now it kind of like, as long as something knows how to load a symbol, right? You just need load. So, but in the end, load ended up in func. I'm not actually sure load's going to stay in func, but it's there for now. I've been toying with the idea of moving load and store into the core extension just because what's a symbol if you can't load and store it? But it's got complications associated with it. So anyway, I'm going into a little bit of depth there. All right, here's, I don't want to go too long here. Here's an example of the const. So const takes, the builder that you're supposed to store this constant operation into and the literal that it's going to operate on. This is creating an operation. An operation is part of the IR, so it needs to use the allocator that's attached to the IR object that we're that we're using for this builder object. The idea here is that you can have a single allocator tied to a particular bunch of IR. So you could, if that's a sort of bucket that you could do a mass destroy on, then you could, if you don't need that IR anymore, you can just bulk free it and be done with it, and all of the IR is attached to the same allocator. In principle, this allocator is still a raw allocator, so it's using malloc free anyway. But in future, it could become much more useful. So to produce results, you have to create values. Extensions are allowed to create values. Not everyone is, like, outside of extension objects. You're not allowed to create values willy-nilly. It's part of it's a fundamental enough part of the IR that you're not allowed to create your own values. But an extension can do it. So it creates a value that's associated with this builder and has the type of the literal. And then that result, and then it uses a constructor on opconst is the class that knows how to create that's associated with a constant operation. Among the things that you pass to it is what is the ID of the const action, and what is the result value, and what is the source literal for the operation, as well as some other stuff that gets passed in. And then, again, not everybody can do this, but extension objects can call add operation on a builder in order to insert an operation into the builder. So there's a few controls over how IR objects can get created and manipulated, and extension objects are one of the more powerful guys who can go along and create all of these things and tack them all together. But the idea is that not just anyone can come along and start mucking with the IR. And I guess I can show you opconst at some point, but let me go a little bit further here still. Let me skip over this piece just a sec. I'm going to get to the add function. So add is one of the ones that has validation checking implemented for it. It's probably the first one that I implemented validation checking for. So here's the code that I was talking about before, right? It's looking to see if how many checker objects there are. And if there are, it tries to validate the add using one of them. And if anybody validates it, then that's good. So it considers that to be valid. If something is going to, if any of these validate functions fail, like if they actually say, no, this is a bad combination that's not supposed to be supported, then it will automatically call that fail validate add. Now I'll show again. We'll go back up and look at what validate add looks like in a sec. This is just kind of a canonicalization thing. So if I don't know why I did it quite right this way, but anyway, it's canonicalizing add so that addresses are always on the left.
How does the order of those checkers get defined so that, like, you can imagine, the first checker says no, you can't do that, but there's a better one coming later that says yeah, that's okay.
Yeah, well,
you don't
exactly.
want this one to fail.
Yeah, so I'll show how that works in a sec. Okay. Basically, it goes in kind of a reverse order. So the validation checker associated with the base extension is the guy that goes last, and everybody else is supposed to let it flow through if it doesn't recognize it. So it's kind of a say yes if it's good, otherwise say no. And then the base extension checker at the end, if nobody said yes, it's a fail. So I'll show that in a sec. Right, so this is just a canonicalization step here, and then if everything gets to here, that means that the left and right operations values are valid, and we can create it. So it creates the value, creates an op add, which is the class that corresponds to an add operation, passes in all of these guys, adds it to the builder object B, and returns the result of the value, the result value that got created. All right, so let's go back and check that thing that I just talked about here. So this is the base extension checker validate add. This is the last one that will run. If there are other checker objects, they have to go first. And their purpose is to validate if any aspect of the values being passed in is a type of their type, then they're responsible for, like, if the complex extension saw a left value that was complex or a right value that was complex, then it's responsible for validating that operation. Otherwise, it's supposed to leave it alone. So it can say yes, but it can't throw an exception. Or yeah, it can say yes, but it can't throw an exception unless it sees something wrong with one of its types. Sounding more complicated as I go. Sorry, I'm not saying this very succinctly. In the case of this one, so it pulls off the types of the two operations. It needs to do some comparisons with address and word to get this right. And then it just does some validations. So it says, you know, if the left type is an address and the right type isn't word, then that's not a valid combination. You can only add a word-sized integer to an address. And similarly, the other way around, right? So you're allowed to add address to int or int to address, and then that code that I showed before will canonicalize them to always be address plus int or whatever, word. And then if it's not an address-sized thing, then if it is one of the primitive sort of numeric types, i.e. 8, 16, 32, or 64-bit integer, or 32 or 64-bit float, then the two types have to match, and if they don't, then it will fail. But if they do match, then that's a valid one, so we return true. And then finally, if it falls through to here, that means we haven't seen a set of types that we like, so it must be bad, so we fail validate add. And then that fail validate add, its sole purpose in life, it gets the same basic signature as the creation of the operation, so it sees all of the operands that were passed in. It creates a compilation exception using the base object's compile fail bad input types add, which is one of the compile return codes that we registered. And then it tacks in a bunch of information into this exception object that it's created, and creates a message that tells you where things are. One of the first things that gets displayed when this error message is, or when this exception message is printed out, is the location, which is this guy that got passed in. So you notice that it got passed into the creation of the exception object, so the exception also knows exactly where the call was made from and can report that to the out as part of the message. And then it throws it. So at that point, you're bailing out of everything. When you call compiler compile, this whole building of IR process is happening inside a try region. So that's the try region that catches it and then passes back, grabs the return message and returns that to the compile call. And then you can also get access to the exception object if you want to at that point from the compiler to get all of these details. Did that make more sense, Keith?
I know that all makes sense. I'm wondering, this sort of dies at the first failure, so it doesn't sound like you'd want to build a real compiler out of it that reported the first 100 errors before giving up.
Yeah, I guess that's sort of true. I guess it doesn't work in the case of a static compiler. You're right. It's more aimed at the sort of JIT compiler notion where, once I've got a problem, it's screwed. So I need to fix that problem. I mean,
yeah, we don't have anything kind of worth executing.
Yeah, there's no fallback anyway, so yeah. You're going to have to fix that. So, yeah, but you're right. That is kind of a mode. I guess. Let's see. Is there a way I could fix that? Not easily. Not as easily, maybe. Anyway, I think about that. It's a good point. Thank you. Right. Okay. So that's add. Then there's like all the different ones. Convert to is for converting a value to a different type, which is sometimes valid and sometimes not. Multiply, subtract, all have these validations. Here's the for loop one you can look at. Right. So again, there's a validation for the for loop, which in this case, I think validate for loop only does, Oh, it does allow counters to be everything. Okay, so any integer type basically you can use for your counter type if you want, and then it assumes that all of the initial, final, and bump are exactly the same type that you said it should be. I don't know why I didn't use counter type here, but anyway, we'll fix that later. So basically, you have to pick an integral type for the loop counter, and then it will count based on that. Now, I mean, I guess in principle you could use a floating point, but because this one's currently using the underlying OMR the IL that it generates with JitBuilder needs it to be an integer iteration variable. So when I create an extension that goes directly to the OMR compiler or to the OpenJ9 compiler, then it can be a floating point. You could use a for loop like in the same way that C does, and just generate a kind of a while loop that would also work with floating point values or any numeric value really. Yeah, so once it validates that these values are all make sense, then it creates the loop builder object, stores the things that were passed into it, and then creates the opt for loop class. As part of this guy, it gets past the loop builder, and that class will actually create the bound builders for the loop body, for the break builder and the continue builder, and store those into the loop builder object, so that once you get the return from this for loop up, it's just returning it. It can people know where to insert operations to make them run in the builder, and if they need to execute a break, they know which builder to branch to, etc., or to continue, and so on. So all the if CMPs have their, again, validating if CMPs are all doing the same basic kind of thing.
Sorry, can you go back to loop builder again?
Sure.
What is?
Sorry, I know I've been going very quickly.
You're creating, so for line 467, so loop builders,
yeah,
that's being allocated on the stack?
That one is, yes. Notice that it's not passing a pointer back. It's making a full copy of the object, just so you don't have to manage the memory.
Got it.
Yeah. Because it's really just a set of values, so it's like a multiple return value, basically, a way of returning multiple return values. Is there anything else I want to see in here? These are all the FCMPs. There's probably not anything else in the base extension that's interesting. We're at 307. I mean, there are a bunch of other classes that I could show. There's types, there's symbols, there's operations. So I guess I'll say, is there any one of those that people in particular would like to see one of?
What were the choices? Types?
Symbols, types, and operations. So you can see what one of the operation classes look like, or one of the symbols classes look like, or one of the base. I don't even remember what base symbol there is, to be honest.
Sorry, when you say operation, is that different from add?
Yeah, it's the class that actually represents an add operation.
Oh.
So it's not like in Testarossa you have tr node and everything just goes into tr node. In JV2 there actually is a class there's a subclass for every kind of IR thing. It's a different way of doing it. Slightly more painful way, but it's a more extensible way.
I'll request types then.
Types. All right. Any other votes on the phone? All right. Base types. So similar thing. It's all in the base namespace. It knows about base extension, but doesn't do anything here. So, okay, what did I do here? So there are obviously a lot of different base types that the base extension created, like int 8, int 16, float 32, blah, 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 blah. All of those types in this particular extension, I created a base class for all of those types, just to be able to reference them all. So I called it base type, very unimaginatively named. And one of the most common feature of this is just that it has, so every type object has the extension that was used to create it cached in it, but it's represented as an ext as an extension, not as a base extension. So this guy just provides a way to get a base extension pointer or a const one. So it's just a static cast basically to base extension. And then the next subclass of base type is a numeric type. So all the integer and floating point types are going to be subclasses of numeric type. I don't actually take advantage of this subclass right now, but it seems like a reasonable subclass to have. So it creates that type. And all of these are represented in the kind service. So you can ask a type if it's a numeric type, if it is kind numeric type, or you can refine it to a numeric type. So if at some point some API ended up being added here, like maybe 0 or 1 literals, something like that, it could be put onto this this class here. Then on top of numeric type, there's an integer type, and lower down there's a floating point type, which just basically it introduces some new functionality there, which isn't very useful, to be honest, because it has to be an integer type before you can ask if it's an integer. So vestigial, we'll call that. And again, nothing else takes advantage of it. And then we get into the actual concrete type. So int type is an integer type. Here's how the allocation works. It's a lot of these things I use the friend class so that the base extension can create it without having a public constructor, so nobody else can construct it, but the base extension object can construct it because its constructors are protected. And then there's a bunch of virtual function API that that type itself introduces. So we haven't seen it yet because it was all hidden underneath base type. The superclass type of base type had this type. So you can ask what's the size of a value of this type. You can, in principle, you can ask for a literal of a particular value, and in this case int 8, because so this one, it's virtual going forward, not virtual inherited from anybody else. 0 is the same way. Identity is the same way. Identity actually is one of the ones I think that it inherits virtually. Literals are equal is an inherited virtual thing. So if I have 2 values of this type and L1 and L2, the type can tell me whether or not they're equal. The reason why you need this is because literals are there's only one literal type. You don't, or literal class. There's no you know, int 8 literal, int 16 literal, int 32 literal. Literal is just literal, and then it uses a pointer to a raw bytes to hold the actual literal value. And then the interpretation of that thing depends on what the type of the literal is. That's how that's managed. It's just basically, so if you had a struct, you could imagine a literal struct, which is a bag of bytes that a literal has a pointer to, and then the struct type of the literal knows how to interpret the bag of bytes, basically.
I noticed.
Sorry, was there a question?
I don't see anything about signed versus unsigned here.
Yeah.
As I remember near the beginning in your talk, you listed a bunch of, you know, the compare versus compare unsigned. And,
yep. Yeah. So that's a decision that I inherited from what we've done with the Testarossa IL, in that we consider signedness to be a property of the operation, not a property of data. Which is, it has pros and cons.
Well, if you're talking about the bag of bytes, yeah, the interpretation goes with the type, but I don't see a way to represent the 2 types. One that says these 4 bytes represent a signed thing in big endian order versus this one that says it's unsigned in little endian order. Or
right. It is because it's the operation that knows the type, not the data. Because the bits are just bits. So it's one way of looking at the problem, Keith. You can either consider signedness to be a property of the data, or you can consider it a property of the operations that process the data. And the way that we decided to do that in Testarossa in the end was to make it a property of the operation. So you do unsigned operations on data bits that interpret those bits as unsigned values or signed values if they're signed operations.
Yeah, but I don't know, maybe I'll push my example a little further. Which byte has the sign is part of the type then, or you kind of mix all this into all these operations. And so now you've got a add signed, add unsigned, add signed little endian, add unsigned little endian, and so on. And it,
well, you would have you could have add big endian and little endian, but you wouldn't have add signed and add unsigned because there's actually no difference in the instruction that you would use to do those.
I suppose, given your the stuff you showed us earlier, where the types have the same sizes.
Right.
But I think I don't know, maybe I'm not sure which architecture I'm thinking of, but there are different adds.
Right. So there's a different operation.
Might set different
that's the point.
Bits.
Right. That's the point. There's like, if you look at it from the point of view of the processor, there's no such thing as signed and unsigned registers. There are only signed and unsigned instructions that you run.
Right.
So that same way of looking at it is what the compiler is taking.
Okay.
It's
so
saying there's no signed and unsigned data. There's only signed and unsigned operations applied to data.
Yeah.
So I say, it's one way of looking at it. It's not the only way of looking at it, and it does have pros and cons. You're I'm not trying to say it's provably better than than the other way of doing it.
I mean, you got to make a trade-off somewhere, I suppose.
Right. So we've done it both ways in Testarossa. So we used to have unsigned data types in Testarossa, and it ended up being more painful to manage all of the duplicated, there's a whole bunch of places where you have to check, is this a signed or an unsigned int 8? Is it a signed or an unsigned int 16-bit? Is it a signed or unsigned? Because the thing you were doing didn't care, and you didn't want to limit yourself to only doing it for one.
Yeah, I guess
and that ends up,
as long as you're prepared to have all of the extension operations convert this unsigned 8-bit into signed 16-bit, or whatever combination makes sense, right?
Yeah, I mean, in the end, there's an input thing that you're trying. There's a calculation that you're trying to do, and you just have to find the right way to express that in the IR of the compiler. So it's usually it's at the point where you're generating the IR. There's a right way to generate the IR, and it in an IR that associates signedness with data, you do it one way, and if there's an IR that associates signedness with operations, then you do it another way. But in the end, it's kind of you get it right or you don't at the start, and then the compiler maintains it from that point forward.
Sure. No, I just I'm reminded of other representations like the stabs debug information format. Talks about scalars in terms of a range, minus 128 to plus 127.
So I will say that, I mean, this is the notion of the types that have been created right now. It's not to say that it's impossible to create a signed or unsigned type in JB2. It's just a matter of, making sure that everything else understands what that means when you do it.
Right.
Right, because it is meant to be extensible, and you can add your own types. So, in principle, someone could come along and write the signed types extension, which is parallel to the base extension, which creates int 8, uint 8, and sint 8, uint 16, and sint 16. Right, you could do all of that, and then build a whole compiler infrastructure based on that notation. And there would be some things that would get better if you did it that way.
Yeah, I haven't thought it all through, so
it's one of those 6 of one, half a dozen of another kind of discussions. But that's the side of the trade-off that we've landed on in Testarossa, and that's been you know, kind of inherited from that.
Okay, thanks, Mark.
Yep. Let's see. I was talking about literals are equal. Right. So a type can tell if two of its literals are equal. There's some logging support stuff for logging a value of this type or a literal of this type, which ends up being used by by the logger to generate log output. Because this is int 8 type, it has this get integer thing, so you basically have to be able to refine it to the integer type before you can call this guy. I believe. I don't think this guy exists in the superclass, but I could be wrong. Anyway, these types and this system of types has kind of evolved over time, so there may be some vestigial stuff in here that I just haven't cleaned up yet. And beyond that, you know, that's how you create. All these types have both a constructor that's the way that the actual type gets created in the first place by the base extension object, and then there's also kind of a cloning constructor here, which for the process of cloning the IR and creating a full independent copy of all of the IR, every type, every symbol, every operation, etc., has a constructor that looks like this, which takes an IR cloner object and basically provides a way of creating a copy of an existing object using a different memory allocator and associating it with an IR object. So this constructor says, here's this other int 8 type object. I'd like you to make a copy of it using IR cloner. So it's kind of like a copy constructor, but weirder. And then that's also serviced by this clone operation. So you can ask an object, an int 8 type object, to clone itself using this IR cloner and this allocator. And then all the other types are kind of the same way. You'll see the size keeps getting bigger. Size is in bits, just as a full generality. There aren't any types that are weird bits, but you never know. I haven't done ZOS yet. Here's the next numeric type, which is the floating point type. Again, doesn't really do much by itself right now. Float 32 extends it, and float 64 extends it too. So once you know it's a floating point, you can ask the floating point value from a literal of it. But anyway, these kinds of things all exist. Then there's an address type. There's a pointer type. Okay, maybe I'll pause here and talk about the pointer type builder that does this. The way that pointers get created is through a builder object kind of approach too, as well as structs. Structs is a really interesting one, but I'll start with pointers. So a pointer type has a base type, so the way that the actual pointer type gets created is you create a pointer type builder object. You set what the base type is, and if you need a helper in order to create it, and I don't want to go into that detail. The helper object, the helper thing is basically a way of creating recursive types that reference themselves, right? So if I have a pointer type inside a struct that points to the next field, that's actually not the best example. In fact, I had pointer to pointer to pointer to around. Would that work? Could you create a type like that? Sounds awful. I don't want to type that. The example works better for structs, so let me stick a pin in that one, and let's not talk about the helpers at this point. But basically, you set the base type, so you can. This enables kind of a fluent model, a fluent API model for creating pointer types. So you have this type builder. You take that object, call set base type, and pass a type to it, and then you pass create, and then it will create the type and return it to you. And it's just so in pointers, it's fairly straightforward. The actual pointer types that it creates are actually part of address type. They're a subclass of address type. They have all the same kinds of goodies that the other things have. Ignore that for now. Actually, just ignore that. I don't want to talk about that today. And that's it. Yeah, so it adds a base type pointer here. Note that type pointers are all const, so once you create a type, you can't change it ever. That's kind of by design. It is by design. All right, structs are created. There are both types that represent an entire struct, and then there's a type that represents the fields of a struct. So if your field is an int 8, there's a field type that says, I'm a field that has an int 8 that has this name, and I'm a member of this struct type. So there's all that sort of structure around how struct types are built up. And when I say struct, it's also union, because the offset of the field within the struct there's no requirement that they don't overlap, or that, you know, you can do all kinds of crazy stuff if you really wanted to. But all it does verify, I think right now, is that the size of the struct type, there's no field that extends outside of the size of the struct type. Basically, it constructs the struct type that way. But this is a so field type fields. Every field type knows which struct it's a part of, what the name of the field is, what the type of the field is, and what offset in the struct is the field's at. Right. So those are sort of the basic pieces of a field type. And you can already sort of see the recursiveness of this. Like, the field type needs to know the struct type, and then obviously the struct type is going to have a list of the field types too. So that recursive nature already exists just in a single struct. And then you need a way to be able to create these things and make them const pointers, because all types are const. So so that's where the struct type builder guy comes into play. So this guy kind of basically just builds up a representation of what the fields are without actually creating the field types yet. And then so you kind of you can set the name of the struct. You can add a field, and a field has a name and a type and an offset. But this doesn't create the field type yet. It's only when you actually call the create that it ends up creating the actual struct and field types. And this is where the helper thing makes a lot more sense, because if you had a recursive struct like a list element, it has to have a pointer to this, like the field type has to have a pointer back to the struct type. So it's the same kind of thing. And the helper is a way for you to add. So the helper is called as part of the creation process, but before any of the field types get created. So it's a way to add fields after the struct type has been created. So you're being called in the middle of creating the struct type. So the struct type pointer exists, which you're not allowed to change. And obviously it doesn't have very much information in it yet, but you are allowed to call add field from there to say, I want to add a field that has a pointer. Like, you can create a pointer type that points at the struct type because it's now been created. And then you can add a field that points to that pointer type. And then once the helper is finished, then it will go through and process all the fields that have been created in its list and set up the actual struct. So it's a little bit quirky, but it manages to let me keep all of the types as const, which I thought was a very useful property, and yet still be able to create recursive struct types and do interesting things. Anyway, so yeah, so it has the create and verify and blah blah blah. And I used to think I needed unions, but I don't. So yeah, and then struct type just has this has actually a very old. This thing is, I think, still one of the ones using the standard map. So this this has to get fixed here. We mean multi-map. Look at that. Didn't realize I was using multi-map. Damn it. 2 more SDL containers to get rid of.
You got a couple minutes left.
Yeah, I'm gonna wrap up there because that's kind of the end, and I do have a meeting in 2 minutes. So every one of these presentations has gone for 90 minutes, so my throat is getting raw as I'm talking through this. I hope that was useful for people and you found it interesting to see the code. I guess one other thing I'll point out, although I have a counterexample on the screen. Where do I have it good here? I mean, one of the other things that you get a flavor for in this is the code formatting that I've been using for this whole code base, although obviously not consistently because there's a counterexample here. But where I ended up falling into the Testarossa scheme. But anyway, for the most part, I'm using the this slightly more succinct bracing scheme, whose name I always forget, and I'm using 4 spaces, so I could not bring myself to use tabs, but I did try to make I did kind of look at what the coding format recommendations were out of the last time we discussed it and try to do something that looks more or less similar. So, anyway, I've gotten used to this. But I can still read Testarossa code too, so, and I can read J9 code too, so I'm not the determining factor anymore. Anyway, I'll wrap up there. Any quick questions at the end? Okay, well, if anything occurs to anybody, if you want to talk to me about anything, if you have suggestions or ideas or, I don't know, critiques, please feel free to reach out. I'm always interested to talk about JitBuilder too with people.
Okay, thanks for taking us through that, Mark.
Yep.
Okay. All right, see everyone in a couple weeks.